Okay, so in the previous video itself, the graphs that we previously mentioned is mainly for your transverse wave. And for displacement time graph, both transverse and longitudinal waves look like this. However, for the displacement distance graph of a longitudinal wave, we actually need to know how does the longitudinal wave move first. And therefore, it's easier to draw and visualize how it is different from your for your transverse wave, because the transverse wave will look exactly like how the wave travels. So this looks just like the wave itself. However, the way that the longitudinal wave move, because we know that it's actually in the perpendicular direction itself, how do we draw a displacement time graph in that sense then? Okay, so basically what we're gonna do is we'll draw 13 lines with equal spacing between them, and you see all these dots. These purple dots represent the particles when there is no wave that is causing them to move about their position itself. So you can just imagine when there is a wave, this one will move here, this one will move here, this one will move here, this one will be center, this one will move here, this one will move close like this, and this one in the center, this fella move here, this fella move here, and this fella move here. This is in the center. Okay, so you can just imagine that there's particles here, particles here, particles here, particles here, particles here, 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 and here. Okay, so you can just see if I were to draw, okay, let me just grab my ruler out. If I were to draw a horizontal line that represents the distance per meter, and my horizontal, which represents the displacement per meter. First things first, the first particle is not displaced, right? So it has a zero displacement. And if you notice, this here is actually the largest displacement to the right. So you can just draw and fill in. This is the minimal negative, because if you notice, it's now in the opposite direction. It's pointing to the left, right? This, we are taking rightward displacement to be positive. So any leftward displacement like this is negative itself. This is zero again, this is zero again, this is positive again. So if you were to draw and connect the dots itself, it will look something like this. Okay, look something like this, like this, like this. So you can see it forms that sinusoidal shape. However, I want you to take note is that this point is the maximum. Okay, so you can see actually your maximum displacement is actually not at the what we call a compression. This is what you call compression. This is what we call a rarefaction. This is what we call compression itself. This is what we call a rarefaction. Now, compression, normally when you say, for example, this is a sound wave this is air, right? So when you compress air, you can just imagine that there's more air particles together, right? So you can see where there is 3 particles, the air is much more compressed itself, and that is actually not the maximum displacement. So you can see the displacement time graph is actually a bit different, because by right, the compression should be at the maximum point, right? But your compression is actually at the equilibrium position, because that is the point where there is more graphs drawn. So my drawing isn't very clear, so let's take a look at the one that is actually prepared beforehand. So you can see, because of the wave that travels itself, there will be a point where there is more particles, and this point is what we call your compression over here. So this point is where air is compressed, and then if you notice, there is a point where there's actually no air particles, or just one air particles by itself. This is what we call rarefaction. So basically, this is your minimum and this is your maximum. That is why typically for a longitudinal wave itself, we don't actually represent it with a displacement distance graph. We will use another graph called a pressure distance graph, but that graph will be covered in the sound chapter itself. So for now, just understand this and how it works, and know that basically if you are expected to know because there have been IP schools or even some of the more difficult O-level non-IP students, the school papers, they have actually tested on this before. So because this was not part of the notes that is printed in the textbook itself, so you will have to actually draw it itself. So if you need to, just pause the video here and you can try to sketch it out on your own. Make sure to label everything nicely. If not, you can just do what I have did just now and see if you could just draw your own version and make sense of what is going on. Okay. So continuing on, we'll continue and do the work example here. So from this graph itself, where is the crest and the trough? The crest and the trough is the maximum and the minimum point as well. So you can actually label this one as crest as well if you want to, but you only need to show one of them. Now determine the wavelength. This is a distance graph, right? So wavelength I can actually take from the starting point to the starting point. So the wavelength is equals to 400 minus 0, which is 400 meters over here. And what's the amplitude of the wave? Amplitude, we're going to take from the 0 position and go upwards. So the amplitude will be equals to 10 minus 0, and this is 10 meters. So always double check what's the unit. Okay, so with that, that's how you do and solve question 1. And then for question 2, same thing. Where's the crest and trough? If you want, you can just write crest. If you want, you can write trough. Over here, over here. Now do take note, this is a time graph. So if you want to find amplitude, all we need to do is take from here, go upwards. This is 0.10 meters. Okay, what's the period? Period is your time period. What is T? Time period, if you're taking from starting point to ending point. So start here and here is 2 seconds. Double check the units. So 2 seconds, and now we want to find frequency. Frequency is 1 over T, 1 over 2.0, and now 0.50. Units is capital H, small z, hertz. Okay.